Good afternoon. My name is James Little, and I've created a free NIST GCMS software lab for universities. This is part 1, which is the very basic theory of GC mass spec analyses. The total course or lab is divided into 8 parts that are shown here, and they can be found on my training website shown below. Gas chromatography mass spectrometry is a hyphenated technique. GCMS remains one of the most powerful, flexible, and widely used tools for analyzing chemical mixtures in drug screening, forensic, environmental, and trace analysis, as well as other applications. If you've never done any gas chromatography, I thought I would compare it to paper chromatography. In paper chromatography, you take the mixture of dyes, which is in general would be a black ink, and put it on filter paper. You immerse the filter paper in the water, which is the mobile phase, and as the water wicks up through this paper, it separates the components into their separate colors that's shown on the right here. Gas chromatography in many ways is very similar. In this case, we have a stationary phase, which is coated capillary tubing, which takes the place of the filter paper above. We put our compounds in a flow of helium at the head of this capillary column, and then it separates it into its separate components that can be analyzed by the mass spectrometer. And the compounds are separated by polarity and or boiling point, and one can increase with time the temperature of this column to increase or decrease the time it takes to separate your components. So here is a typical gas chromatography system equipped with an EI mass spectrometer as the detector. As we said, we have helium as our carrier gas. It goes up to a carrier gas flow controller that's set to be constant flow of about a mil a minute of helium. We take our sample, dissolve it in an organic solvent, and put it in a 10 microliter syringe that we inject on this hot injection port, which volatilizes the organic compound of interest or mixtures of compounds of interest plus the solvent. The helium pushes it onto the column where it's separated in this column oven that we can control the temperature, and we can actually temperature program it to decrease the analysis time to get things off quicker. It goes to a detector. Well, the detector for a gas chromatograph could be many different things, but the one that we will discuss is the mass spectrometer, which is probably the most useful or most powerful detector that can be connected to gas chromatography. So we've used the electron ionization mass spectrometer as our detector. All the information that is acquired by the detector is sent to a data processing unit, which is, in our case, the NIST mass spec software that's run on a Windows PC. So, as it gets to the first part of the mass spectrometer, it's the electron ionization source, the EI source. So we have our analyte that's coming in a vapor from GC in helium, comes into the source, it's flowing in, and this is all under vacuum. The whole mass spec is under high vacuum, including the detector that we'll discuss next. This analyte interacts with this electron beam that's put at 70 electron volts. We increase the energy of this by going over to a trap to pull the electrons across to increase their energy that they have in the beam, and this ionizes the compound to form our analyte, shown here as a positive ion. And now, since we have an ion, we can use extraction and focusing lenses with a voltage on them to separate and pull the ions out of the source and send them on to the mass spec detector, which we'll discuss next. In this particular case, we're using a quadrupole mass spec detector, which is also under vacuum. There are many types of mass spec detectors, but the quadrupole is the one that's most used. In the quadrupole mass spec detector, we have 4 quadrupole rods that are put at different RF and DC voltages. So as it comes in from the ion source, we change this RF DC ratio of voltages. And when you do that, you can set it so that only one ion at a particular mass to charge can go to the detector. All the other ions either strike the quadrupoles or fall outside the field. So we change this RFDC ratio many times to detect all the ions in the compound. So we send one mass to charge value to the detector at a time. And you can somewhat simplistically think of this as a Dalton. To separate by Daltons, it's really mass to charge, but in most cases, the charge is 1 in an EI source. Occasionally 2, but most often you can think of it as being a charge of 1. So it's really giving 1 Dalton at a time to the detector to be detected. And the quad starts at mass to charge 10, and it goes to 11, it goes to 12, all the way up to 800 in steps of 1 Dalton or 1 mass to charge unit. And it does this whole cycle in 1 second to get the scan for the mass spectrometer. And the scan rate of less than 1 second is fast enough to get several spectra across a GC peak for one component. These mass to charges versus intensity pairs, there's a pair of them, is stored on the PC separately for each pair for processing with the NIST software, and that corresponds to that scan or that point in time. Here we have the Agilent MSD quadrupole assembly. You can see it's a very compact unit, so the overall instrument's relatively small. As you can see you can see someone holding it here to get an idea of what the size of the quadrupole actually is. So what do we get from this quadrupole and ionization sort? Well, we get a mass spectrum, and what we'll discuss first is the mass spectrum of acetone. These spectra are very reproducible, thus they're easily found in spectral library searches via computer, and that's what the NIST software does, which we'll discuss later and demonstrate. So we start out with our molecular weight of our compound. It's 58. It interacts with this 70 electron volt beam of electrons to give a molecular ion, which will be at mass to charge 58. But this excess energy that we've imparted to the molecule makes it fragment into mass to charge 15 and 43 and many other ions. So this is what it looks like when you plot these mass to charge versus intensity pairs, the relative intensity versus mass to charge in the data system. We'll have the mass spectrum, the EI mass spectrum of acetone. You can see it has a base peak of 43, and it has a molecular ion peak at 58. Also has the 15 ion for the methyl group. But there are other small ions here. The ratio of these small ions to the large ions are very reproducible, again leading to the ability to computer search this spectrum versus a reference database. But there are some other small ions in the spectrum, and that's due to the isotopic ions from the presence of C13. So these small ions, like at 59 and 60, 43, 44, etc., are from the carbon-13 present. Carbon is an A+1 element. That means that its abundance, A, is shifted by 1 Dalton, or 1 mass to charge unit in the mass spectrum, because there is C13 present, but the ratio of C12 to C13 is relatively small, so the ratio is 100 to 1.1. So these ions are relatively small, but in this case we'll just discuss them. The first one is the molecular ion, which was acetone, where all its carbons are carbon-12. The 59 would be with 2 carbon-12 atoms with 1 C13 atom. And the very small ion, showing the probability of having two C13s in one molecule, is relatively small. We'd have 1 carbon-12 atom and 2 C13 atoms. Let's take a look at another EI mass spectrum, that of methylene chloride. It'll be much different from carbon-containing species that we'd noted before, like acetone, because it has chlorine-37 in addition to chlorine-35, and the chlorine-37 is very abundant, relatively speaking. So it will be easy to find in a computer search, and also will be easily noted when you're looking at the mass spectrum. The ratio of chlorine 35 to 37 is 100 to 32. And again, in this case, it's not an A+1, it's an A+2. It means that it's shifted 2 Daltons when it's present, when you see that ion, as opposed to carbon, which is an A+1, that shows up at just 1 above the molecular ion. So here's the mass spectrum of methylene chloride. Again, we see an abundant molecular ion here. In this case, it'll be for CH2 with 2 chlorine atoms that are chlorine 35. And 2 units over, you'll see one at mass to charge 86, in which we have a chlorine 35 and a chlorine 37. And even further over, we'll see one that's now, we're at 84, 86. This will be at 88 due to the presence of 2 chlorine 37 atoms and no chlorine 35. So you can see it's a very distinct mass spectrum. You can still see the presence of the A+1 element because we do have CH2, we have 1 carbon, so you will get some abundance due to this A+1 in addition to the A+2 elements. So again, this is very useful in that isotope ratios are useful for determining or getting an idea of the elemental composition of a compound. So what are the natural abundances of some stable isotopes? Well, here's a common ones we have here, hydrogen all the way down to iodine. And you can see their A abundance is always set at 100, so you get the relative ratio. And for carbon, as we noted, it's 1.1. So the ratio of carbon 12 to carbon 13 is 100 to 1.1. For the chlorine we just did, it has a mass, most abundant mass, at 35, which would be the 100%. And then at 37, we had the 32%. And as we said, it's an A+2 element, while carbon is an A+1. Nitrogen is an A+1, but the abundance is so low it's not very useful for determining the elemental composition on a quadrupole mass spectrometer. We do have oxygen, again, is not very useful. Fluorine is monoisotopic, so it's 100%, but doesn't have any significant stable isotopes that we will see. Silicon goes up a little bit, it's 3.4%, it's a +2 element. So you can see chlorine is very distinctive. Sulfur, not so much. Silicon, not as much. Bromine, very distinctive because it's an A+2 element, that its abundance of its molecular ion for bromine 79 is 100, and for 81 is 97%, so it'll be very large. And there are some other monoisotopic ones that do not have any significant isotopes, such as iodine and phosphorus. Here's some patterns that you would see. For 1 chlorine, you'd see an A+2 that has this pattern, and you can see as you go up with more and more chlorines, you get different patterns. And if you can look at this table, you could tell by looking at the molecular ion the ratio of the chlorines, the number of chlorines present, but also if bromine was present, you could see the mixed ones. This would be a very distinctive isotope pattern. And I'm not saying you really need to use these all the time, but just realize when you see something like this that you do have an A+2 element. And of course, the computer will be easily able to use this isotopic pattern in doing the computer search to give you a good identification. Again, we have some here for sulfur. I wanted to show you over here, this is an isotope pattern that they've generated for one that has 10 carbons, 2 chlorines, and a bromine. And you can see, again, we do have some carbon in the compound, about around 10% of this ion with respect to this ion for this pattern. But again, very reproducible mass spectra that can be useful in library searches and just if you want to manually interpret a mass spectrum. Unfortunately, not all compounds have a molecular ion. The molecular ion is not stable, and it immediately fragments. And this is due to the compound coming into contact with this 70 electron volt beam from the filament. So it immediately fragments to lose a methyl group to form the 227 ion, and likewise loses a bromine to form the mass to charge 163 ion shown here. However, it's still easily identified by a computer search. Here we have the EI mass spectrum of the compound. As we said, no molecular ions seen, but if you blew this up, you would see a good isotope pattern for the loss of the methyl group. And here is the 163 ion where it loses the bromine group. So to say again, it's still easily identified by computer search and actually easily interpreted if you can determine what the molecular weight of the compound is. So when we put it all together, we've got the separation with the gas chromatograph. We go into the ionization source to ionize it. Then we go to the quadrupole, and then we count the ions to get the mass spectrum. So this is what you get out as far as the total ion chromatogram. And if you look at it, ions at each spectrum, at each scan, are summed, giving a total ion current. And we take this total ion current and we plot it on this axis here. And then on this axis is either time or scan number. So in this case, during this experiment, we attained about 2,500 mass spectra because we had around 2,500 scans. And we plot as an intensity versus time to get this total ion chromatogram. So what does it tell you? Well, you can just start counting the peaks, 1, 2, 3, all the way up. And I counted, and I got about 130 peaks in this chromatogram. So it's a very complex mixture. But just because you get a peak doesn't mean it's separated all the components. And sometimes you can see it starting to coalute. So this peak was not resolved from this totally. So each peak does not have to be one pure component in a complex mixture. But the data system can display the EI spectrum for every scan or a point in time for the computer to search or for you to try to interpret. It can also deconvolute overlapping components in a peak to get pure spectra out of components that are not totally separated in time or by scans. And then you can take any of these EI spectra that have been deconvoluted and send it to an EI library of 1.2 million spectra. In our case, we'll only have around a little over 2,000. That's what NIST gives you in the demo program. But if you had a regular commercial library of maybe the EI of NIST plus Wiley, it would be around 1.2 million spectra. This library is searched in a few seconds for proposed identification, and I must stress proposed. So you get results very quickly. The identification then must be used with sample history or knowledge of organic chemistry to confirm. So you use the initial identification and then you use additional information to decide if it's a reasonable identity. So I thought it would be useful to show you a few videos that talk about GCMS, and these are two particularly good ones. So they don't take much time, and I've attacked them on the end of my lecture here so you can view them. They'll just keep playing after I get off talking to you, and then you can look at them. So I think they would be really good at reinforcing what we have discussed in the lecture. So take that time to take a look at them, and I hope you found the lecture and the videos very useful as we start to use the NIST Mass Spec software in the next 7 sessions. Good day.
GCMS is an analytical technique used in a variety of different forensic disciplines. For example, drug chemistry, toxicology, and trace chemistry. A chemical analyzer is used to detect and identify chemical compounds of interest, which can include drugs, poisons, fire debris, explosives, or gunshot residue. But what exactly is GCMS, and how does it work? This video will briefly explain what both are and how they are applied in forensic science.
Gas chromatography, or GC, is used in forensics to separate a sample into its individual chemical components, in some cases isolating all of the forensically relevant compounds from one another so that individual chemical identification can occur. The forensic scientist must first perform one of many sample preparation techniques available to make the sample suitable for GC chemical analysis. Most of these preparation techniques involve dissolving the sample into an organic solvent. After sample preparation, a microliter amount of the prepared liquid sample is injected into the injection port of the GC device, where it's immediately volatilized and mixed with a carrier gas. This gas serves to move or push the solutes forward down the capillary column in what is known as the mobile phase. This column provides a surface for the components in the sample to interact with. This is called the stationary phase, and it allows the components to slow down, allowing for separation to occur. The different chemicals in the sample separate based on their volatility and mass. Each peak that appears within the total ion chromatogram represents a different organic chemical component. Mass spectrometry, or MS, is used to produce spectra, or unique spectrum, of each of the individual components within the sample, thereby providing their chemical identity. MS works by ionizing chemical compounds to generate charged molecular fragments and measuring their mass-to-charge ratios. After passing through the GC column, the molecules are blasted with electrons at 70 electron volts, which cause them to break into unique fragments that turn into positively charged particles called cations. These ions travel through an electromagnetic field that filters them based on their mass. The particles must be charged to pass through the filter. The instrument's detector amplifies and then counts the number of ions associated with that specific mass. That information is then sent to a computer and a mass spectrum is created, showing the number of ions with different masses that travel through the filter. Using a computer algorithm, this generated spectrum is then compared and matched against the library database containing known chemical MS spectra. If a match is found within the spectral database, the unknown chemical is identified.
Welcome to the gas chromatography mass spectrometry video, abbreviated as GCMS. The objective of this video is to describe the components and function of a GCMS. This is a GCMS composed of an autosampler, a column oven and column, a mass spectrometer, a gas cylinder. Not shown is a computer that controls the GCMS and collects data. The autosampler allows for fast sample introduction, as well as multiple injections done by the instrument itself. Here is the sample tray. Note that each position is numbered. Position numbers on the autosampler allow us to tell the instrument when and what sample to inject. This is the injection needle. It is programmed to rinse the needle between sample injections. For how to do manual injection, check out this link. The autosampler selects a vial and positions it under the injection needle. The autosampler proceeds with washing stages before it injects the sample. The needle withdraws sample at set volumes for injection. The oven and column are the most important part of any GC. The insulated door must be closed when the GC is on. The oven keeps the column at the required temperature. Columns in GC are typically open tubular columns that have an inert gas as the mobile phase and a bound liquid as the stationary phase. The column stationary phase dictates selectivity. Temperature can also affect elution time. We can alter the time molecules take to elute by altering the temperature or creating a temperature program. Here is the sample inlet. This is where the sample is introduced to the column. Here is the sample outlet. This is where the sample moves from the column to the detector. The mobile phase runs from the start of the instrument, through the column, and to the detector. This instrument uses a mass spectrometer as a detector. The mass analyzer is a quadrupole. It consists of 4 rods that have alternating voltages applied to them. Only selected mass-to-charge values will have a stable path through the rods and then are counted based on their relative abundance. Here is an example of what the software looks like. This is what you would obtain from the GCMS. The top is a chromatogram showing relative abundance on the y-axis and time on the x-axis. A peak appears when a molecule elutes at a specific time from the column. The bottom is a spectrum showing relative abundance on the y-axis and mass to charge on the x-axis. This tells us the mass to charges detected for any given peak.